Thank you so much for the introduction. And I have to say I'm really thrilled to be here. I've worked for a few years now with all these methods, and almost all of them have been developed in this building by people who are in this room. And I'm really thrilled to be able to talk to you guys. And also, I really enjoy this workshop. I'm starting to see that there's a lot more similarity between, say, climate science application and brain imaging, for example, in terms of numbers and variables and some of the tools to use. So that's already been quite useful to me. So I'm going to talk today about two applications of causal discovery in climate science. And I'm more in charge of the methodology, and I work a lot with the climate scientist Yi Deng at Georgia Tech. So if you have any specific questions about climate science in this talk, direct them to Yi. He's the expert, not me. And also, I do realize it's 2 p.m. right after lunch. It's my job to keep you awake. I'll try to do my best here. So, OK. Just a quick overview. I talk a little bit generally about causal discovery in climate science, and then two different applications. The first application is really a warm-up exercise. It only uses 4 variables, and I'm using it to show you the methodologies that we're using. And then application number 2 is really the big one that I want to spend most of the time on. And then we have conclusions on future work and a wish list for causal discovery research. So first of all, first questions. Why do we want to use causal discovery in climate science? Earth is a complex system, so sure, we know most of the basic equations governing the Earth, but there's still many, many effects that we really don't understand. So that's on one hand, we have many open questions, and on the other hand, we get more and more data every year. We get observed data, and we also get the output of climate models. So more and more data, still open questions, sounds like a perfect application for causal discovery. So, and also, I see my role in causal discovery as digging through all of this data and coming up with potential connections. So I'm just looking at it and I say, these are potential causal hypotheses. Then I'm turning it back over to the domain expert. He looks at it and says, well, this looks more like a common cause maybe or not. So basically, we're always trying to find physical mechanisms that support the hypothesis that we found. And if we find them, we think we're right. And if we don't find them, we think that probably we're not right. And there's plenty of opportunity here. So I do miss my pointer here. My thing doesn't work. So anyway, so first of all, in both applications, we use a PC algorithm, clearly developed by Spittis and Glymo in 1991. And whenever I cite it, I always wonder whether, when they called it the Peter and Clark algorithm, whether they would know how often it would get cited. And how many people ask me, why is it called the personal computer algorithm? Like, no, it's the Peter and Clark algorithm. Anyway, so the key point, as you all know, is the PC algorithm can't detect hidden common causes, so we can't prove any causal connections due to the potential of common causes. But we can disprove a lot of them. So what we're doing basically is we're doing an elimination procedure. So we're trying to eliminate as many causal connections as we can until we are only left with a small set of causal hypotheses that we then turn back over to the domain expert. So it's kind of prioritizing what the person should be looking at and coming up with interesting hypotheses then. And so again, for each hypothesis that we get with our methodology, we turn it back over to the domain expert, and then we decide, is this a direct connection? Is it due to a common cause, hidden common cause, or maybe a combination of both? OK, first, just quickly, some literature. The most relevant papers are those two for my work by Chu, Deng, and Glymo, and Chu and Glymo. Other people have used Granger approaches for time series and climate data. So it's two mainly. And there's been a lot of other structural learning in climate science using dynamic or static Bayesian networks. Most of those down here have been more trying to predict things, not that much for causal modeling. And after I put these 9 papers on here, I just took account of how many of those actually come from CMU. It turns out 4 out of 9 actually come from here. So clearly a lot is happening right here. So the first application deals with a very simple first problem. Given us daily data for 500 millibar geopotential height, and whenever I talk about geopotential height at a certain pressure, what that means is you're looking at the Earth and you're asking, OK, at what height do we have that pressure? And that's just something very convenient that climate scientists like to use. It's a function of both temperature and pressure, and it's just very convenient, and that's what I'm going to use the whole time. And there are 4 compound indices that we're interested in. WPO is the Western Pacific Oscillation, EPO, Eastern Pacific Oscillation, PNA, Pacific North America pattern, and NAO is a North Atlantic Oscillation. And all you need to know is just these are 4 compound indices. And we just want to know what could be the potential causal relationships between those 4 variables. So up here is the data, NCAP, NCAR, V-analysis data. You get that for free from NCAR. We only use data from October to March because the signals tend to be much stronger in the wintertime. And so we have roughly 10,800 samples if we use daily data. Now the first model we tried was actually a static model. And in static models, you can't use the daily data because there's just too much noise in there. So usually climate scientists use monthly data, and all of a sudden you're down to just 360 samples, which really isn't a lot. And not surprisingly, it did not work out very well. Our models basically, if we changed alpha, we got the significance level in the PC algorithm. We got inconsistent switching directions and stuff like that. And we just realized in general, time is a very important component, and we get a much better model if we move to a temporal model. So we use the PC algorithm for a temporal model, and I'm using here a procedure that's not new. That was already in this paper, for example. It has been used by other people too, but it doesn't get used a whole lot, so I thought I would give everybody a quick introduction of how this works. So basically, I have my daily values for my 4 different variables here. Let me just step back here a little. For my 4 different variables. And the first thing I do is I choose how much time do I want to have between my time slices. So in this case, d equals 3 days gave the best results, but we tried 2, 1, 4, 5, and 3 turned out to be the best one. And I can give you more feedback if you have questions about why we think that is. And then you choose how many time slices you want to have. So maybe you go from -m to m. So that would be 2m plus 1 different time slices. So we go ahead, we take our original variable, say EPO, and then we start out, we have EPO minus 21, minus 18, minus 15, and so forth, all the way up to EPO 21. So for example, EPO 0 is the same as EPO. EPO 3 is the whole time saying lagged by 3 days, and this is lagged by 21. So I have my original variable, and I define myself, for each one of the 4 variables, I define myself, in this case, 15 different lagged variables. Okay? And I fill them with data, and then I put in my temporal constraints. I say cause can only come before or at the same time as an effect. Cause can never be after the effect. And so I get these time constraints down here. So if EPOI can cause EPOJ and NOJ only if I is smaller or equal to J. Okay? So what I've done now is that I've taken my temporal model and I mapped it to a static model with constraints that I can now plug into my PC algorithm with constraints. And again, you know, if n is the number of original variables I had, in this case 4, and I take s time slices, I now have n times s variables. So I've gotten a lot more nodes than I had before. So now I have 60 nodes in my case. But I can now put that and interpret the time constraints that just put in as constraints in the PC algorithm. I use the standard Fisher z-test. Partial correlations, basically. Alpha is my significance level, D is the number of days per time slice, and S is the number of slices I use. And I get this as the first model. And just to be clear, so WPO, this column, for example, is just the different time slices of WPO. So each column here represents 1 variable. And if you see a link, for example, from here to there, it means EPO minus 3 to WPO 0 means, okay, so it takes 3 days for a signal to travel from EPO to WPO. And I can now go ahead and count, okay, I have this, and I have it again in this next time slice, and I have it again here. So that seems to be a pretty strong link. Okay? What you may also notice, though, and I know these are a little hard to read, those arrows. Can you kind of see them? Yeah, kind of. If you could see it clearly, what you would see is that you have a very regular pattern at the bottom. But in the first few slices, you don't. And in fact, you have a lot more arrows originating in the first few slices. And it took us a few days to figure out why, and it actually makes perfect sense. Because to come up with a good model of what originates from a time slice, you also need a good model of what's going in. And in the first few slices, we've cut that off. So we don't know what's coming in, and that's why we get a bad model of what's coming out. You see more connections than you should. And in most cases, with these 4 variables, you usually have 20% more errors in the first few slices. But it's easy to fix that. The solution is just you build a model with more slices than you want to have, and you just cut out the first few. And with that, you fixed your initialization problem. Yes?
I think I missed one basic thing. What's your sample size now? Or
my sample size for this is a 10,880.
So did you repeat this?
So I have 60 years. I take 180 days in the winter time. So I have 60 times 180. And so what you see, say this one, the WPO0, these ones are basically my original data, right? And this is the same thing, just shifted by 3 days when I feed it in. So I just shifted by a few days. I don't lose any data. I still have my 10,800 data points.
The same data will occur 7 times in the data set.
Yes, that's correct. Yes, it's staggered, exactly. OK, so if I cut off the first 3 slices here, this is my original graph. I cut off the first 3 slices. I'm good. It looks pretty stable. It's pretty repetitive. And I can now go ahead and do my last step, which I need to do, which is just the counting of the errors. So for example, from here to there, well, this is always the same error. So I'm starting to count those now. So for example, from WPO to PNA, I may ask, how many errors did I have that had exactly 3 days delay? And that will tell me the strength of that connection with this time lag. Okay? And I can do that, and then I can put a summary graph here on the right, which just summarizes the strongest connections are here with, oh, they all look dashed now, huh? These are supposed to be non-dashed, and this one is a dashed line, and this is a non-dashed solid line. So what you get now is in one picture all the different connections, potential connections that I can turn back over to a climate scientist, and they love it because it's suddenly all in one picture. They usually only look at one effect. They don't usually look at that as combinations. And you may also see here that we have these interesting little links that go to themselves. And this is, for example, plus 3 or 6 days. And this one is also 3 or 6 days. So what that means is these, we call them intra-mode links. They go from one mode to itself. So from this one to itself or from this one to itself. They tell me how much does for how long does my signal stay there? Question?
So plus 18, plus 9, is that the number of times?
Number of days. Time of days. We're now back into days. And you see only multiples of 3 because I chose my time slices to be 3 days. And it turns out if you go down, if you only take, say, 1 day per time slice, what happens is that you get so many of these links that the other ones kind of get lost in that.
So that the EPO to NAO edge is an effect that takes from the Eastern Pacific to the North Atlantic, it takes 18 days to happen.
Yes, that's correct. That's the hypothesis that we get from this. So, as I said, we have these intermode links that go to itself, that tell us about local memory, how long does the signal stay, how much does this influence itself, so to say. And we have the intermode links that go from one mode to another node, which tell us about the remote impact. And again, I'm showing you that for the simple example where it's easy to explain, because it gets much harder in the much bigger example that I'm giving you later. Okay, so now I'm trying this back over to he, and he looks at it and says, well, okay, does this make sense? And the key question we're asking is, can we find physical mechanisms for each of these things? So he went back to literature and his own knowledge and found that most of those are actually consistent with mechanisms in literature. We know that. But there's, for example, one new link from NAO to PNA with 3 to 6 days lag, and that one we haven't seen before, but they now started to think about, oh, could that be, and trying to test that with a dynamical model. So the warning is still out, but it's exactly what we wanted to have. Most of it fits, and a few new things, and also the lag times. Some of the lag times are new to have specific time lags. So, and that brings me to my second application, which is actually much, much bigger. So any questions so far? Yes?
So the self-loop, if it says 3 or 6 days, that's supposed to be, because you just do 3-day lags, that's immediate in a circumstance.
No, 0.
It basically tells you that the signal goes 3 to 6 days, so you have here's actually here, from here to here and from here to there. What happens if
what's the thought that there's a delay, I guess?
What is the delay? It basically tells you for how much does the state of this variable influence itself. So for how long does it stay there?
But how is there, why is there a 6-day link in addition to that?
Because it influences it, because it's still a strong signal. If you look at, basically what we're doing is we allow everything that comes before to be called influence say on this variable. So the question we're asking is, by which variables is this influenced the most?
Well, I think he's asking by what mechanism. So if I have a mood on Monday, that affects my mood on Tuesday. My mood on Tuesday affects my mood on Wednesday.
Yes, but it turns out
my mood on Monday also have a direct effect on Wednesday.
Well, if you aggregate, the variables right on it.
Hysteresis is one answer. Does that make sense for climate?
Sure. It's hysterical. There could also be some other physical mechanism that has a lag through intervening variables that.
Right. And also, these are compound indices, so they expand over a large geographical area, and maybe something travels throughout that area, and that's why the influence is still felt after a long time. But your question is a good one in terms of, we're really just talking about the strong direct connection. It turns out that, yes, 6 days ago is another strong influence in addition to this one. So even if a condition on this one 3 days ago, this is still important. Okay? Yes?
So clearly there's lots of autocorrelation here.
Yes.
And do the hypothesis tests have any accounting of autocorrelation?
The hypothesis tests, you mean when we're trying to figure out whether these are, no. The hypothesis tests basically look at each one of them independently and try to figure out if they're physical mechanism. They're not statistical tests, they're physics.
So I'm saying the tests that are actually used in the version of PC that you use. So when you're testing conditional independence,
yes,
are you accounting for, do the tests account for the autocorrelation among the data?
Yes, they should, because I'm conditioning on that, right?
You're treating the set
It's because the data sets are staggered. Yes. So you're actually making many copies of the same data set, and you're only regressing on earlier ones. So you're automatically taking into account some of the others.
Yes, because you're treating them as independent variables, basically. Even the previous state of the same variable is treated like an independent variable, except for the time constraint.
It's like addressing an all-model lag, so it's necessarily correlated.
Okay, let's move on about the application I'm actually really excited about. So back in 2004, Sonis and Robert wrote a paper where they defined something called climate networks. And it was kind of a revolution in climate science. There's been dozens of papers on it, but what is it? So it's actually a very simple idea. You take the globe, you put a grid on it, and then you look at the grid points, say the center of each of these little patterns there is a grid point. And you evaluate some kind of atmospheric field. And our favorite field is geopotential height, but you could take pressure, you could take temperature, whatever. And you evaluate that at these grid points, which means that at each grid point you get one time series. Okay? And then you identify all pairs of grid points that have a high correlation. So a climate network is very simple. You take this data, and you just check any pair of variables, totally out of context, checks the correlation. If there's a high correlation, you put a link there. And once that was defined, of course, there was this whole bunch of research on, neighborhood detection and all kinds of methods that you can define for that. So it's a very simple method, but it recited in lots of papers, and it's especially good for finding Taylor connections. So these, I call them correlation-based climate networks. They yield undirected graphs, static models, and they focus on similarities between geographical regions. And that's why they're so good at finding Taylor connections, which are places that are far apart but behave similarly. So they're used to find similarity. And there are two other networks. One uses mutual information, and the other one is a phase synchronization network. But they all use pairwise tests only, nothing else. So of course, when we looked at them, we're like, what would you get if you used causal discovery for that? We had to try this. So again, these ones, the correlation-based climate networks, existing ones, they're really good at identifying things that are Taylor connections, but they're bad at identifying reasons for the Taylor connections. Because you just look at whether nodes are correlated, but not at causal pathways. And as a consequence of that, you don't distinguish between direct and indirect links. And then the last thing is that you get so many links, you can't even print it, so you can't plot the network itself, so that doesn't help either if you can't visualize it. So what happens if you use causal discovery? And our goal was to somehow learn about causal effects rather than similarity. And we had no idea what we would be getting. So our first experiment was, well, static models are always easier. So we start with a static model. And we used an equal area grid. You know, grids are kind of tricky because they always have singularities at the north and the south pole. And so one standard adjustment is to use equal area grids, which means the points don't necessarily have the same distance, neighboring points, but they all cover about the same amount of area. Okay? Yes?
You can sort of uniformly distribute the points on the globe and connect them and that be agreed instead of the standard.
Very good point, and we get to that. Just wait a few slides. So, and again, we use the PC algorithm, tetrad implementation, and this new type of climate network is made as a supplement, not a substitute. I mean, they're both good for different things. So we try it out, and what you see here is a static model, and the blue lines indicate the potential causal connections, and I really wish you could see that better. But still, take a look at it and ask yourself, do those look like causal connections? And just to help you here, we're looking at one side of the globe, and what you should be seeing here are straight lines. And we're looking at the back of the globe, and what we're seeing is hexagons. So do we believe that the causal connections are flowing straight lines on one side of the globe and then hexagons on the other side of the globe? Clearly not. So clearly this is an artifact of the grid, which comes back to your point. Very well taken. I wish I had talked to you before I did that. So anyway.
Which side of the globe has the straight line?
We're at 0 degrees east here. So yes, the Europeans, it's all their fault. Anyway, Germans, So anyway, the Germans have straight lines.
Wait, isn't that Italy also?
They're all in the same boat, so the hexagons in the back. So clearly, something happened because of the grid. And it was pretty clear pretty quickly that whenever 2 points were very close to each other, they were connected. So because if things are, we're looking for the strongest connections, right? So if things are close to each other, there's going to be naturally a stronger connection if they're further apart. So clearly this grid doesn't work for us, because the unequal proximity in the grid is a stronger signal than the actual causal connections that we want to define. So back to the drawing board, we made 2 changes. We decided we needed a grid, a special grid where the neighboring points have the same distance. And if you look at it, it's actually interesting. If you look at distributing points equally on a sphere, you actually can't do that in closed form. So the best thing you can do is an approximate algorithm, and this is a quite efficient one by Verdito et al. And it's so-called cathedral points. You basically start out, you put, say, 200 points randomized on a globe, and you just move them away from each other on each step, iterative step, as if they're repelling each other, and you converge towards the grid. Okay. And the second thing was also, we realized that even when we did that, that still didn't do it with a static model. So we had to move on to a temporal model. So we use now exactly the procedure I showed you for the 4-mode example. We use a Ficata grid. We use daily data. We have about 4,800 samples because we only do 3 months at a time, for example, winter or the summer. We used 15 time slices, and that simply comes from the fact that Yi told me, well, these signals don't travel for more than 2 weeks. So we figured let's start out with 2 weeks and see what we get. So for each of our 200 grid points, we chose 200 grid points because Tetrad couldn't handle more for us. So we have 200 grid points times 15 time slices, so we have 3,000 nodes. So, and then we add the temporal constraints, we start Tetrad, and we wait for 4 or 5 days. Seriously, and I had to run a lot of those, so I went up to 3 in parallel for 4 to 5 days. I couldn't do more than 3. So, and then you get these results, which now are much nicer, and they're kind of okay to see. Up there is which data we used, and these are the results for the Northern Hemisphere. And what's important to say is, okay, these are all the strongest direct connections you get for 0 days delay after we count our errors. This is for 1 day, this is 2 days, and this is 3 days. Let's look at those 2. I turned this over to Yi, and of course I was excited to hear. So does this make sense now? And he looked at it and he laid back and was like, wait, this one is storm tracks. And it's hard to see, but the arrows go this way and here, and then they switch at some point and they go this way. and that's exactly how storm tracks behave. So yeah, we found some physical mechanism. While the ones on this side with a 0-day delay, first you have to ask yourself, well, how quickly can something travel? Because this is quite a distance, and in 0 days, so less than 1 day, it's unlikely that it travels so far. In addition, it turns out that the equator has pretty uniform behavior. So you have pretty uniform conditions usually around the equator, which means it's almost like a hidden common cause. You have the same conditions. So we believe, and in fact, it turns out that over 90% of those edges that we see here, PC actually gave me double error for those that were undirected, and only less than 10% were directed. And we think that's because they're hidden common causes, basically. So for now, we're still looking at that further, but we think that most of those we should disregard as hidden common causes. Yes?
When you say the equator is uniform, it's uniform on any given day, but it varies day to day? Or is it the same every day?
It simply doesn't vary as much as the rest of the globe.
Well, then it would not be a common cause. It would just be a background condition. A common cause would be something that would vary, but it cause everything in the same way.
If it causes everything in the same way, it's still not. What we're trying to see is how does information flow around the globe.
No, I know, but I mean, if it's not changing, then it can't do anything.
Then we shouldn't see anything, is that what you're saying? No errors?
No adjacencies.
No adjacencies?
No. I'm saying that does not act as a common cause of every period.
Okay.
Because it would have to be a varying thing.
Sure. That is a good point.
Could the, I'm sorry, these are days. So each time step is a day. I was going to say this is the common cause, but obviously it's over the course of a whole day.
It's 1 day, yes.
Makes sense.
Well, I have to think about that one further. Thank you.
Sorry.
Yeah, no. That's a good point. So anyway, so these are the results we're getting, and now we're happy because we actually see physical mechanisms happening here. And I now even think even more that I have to return to the 0 days and think more about what exactly these edges mean. So anyway, we think, or at least I thought until a few minutes ago, that the links here are probably due to common cause. I will have to revise that statement. And all other links are storm tracks. You and I would call them storm tracks. Climate scientists call them 2 to 6 day synoptic scale disturbances in the extratropical atmosphere. And so what we see is really information flow around the globe. And so the key ideas here are, what we do is we interpret large-scale atmospheric dynamical processes as information flow around the globe. And then we can use causal discovery to calculate graphs of information flow. So we're extracting that kind of dynamic information out of our observed data, which helps us with understanding some of those dynamic processes. And there's some ways that I can then take the graphs and calculate some properties like the local memory for how long does the signal impact itself, remote impact, average velocity, and so forth. And I just wanted to show you a few plots for winter versus summer and now versus 100 years from now, because then I can talk about climate change. So just in how much time do you have left?
You got about 7.
Okay, great.
How fast is the climate change?
You see a little bit of that, just a little. So this is a plot that shows you just a contour plot of the local memory. So it basically takes the graphs that we have, several of those, and then calculates the local memory, extracts it from that, and plots it in a contour plot for the northern hemisphere. And what you see on the left side is the winter, and from the right side you see the summer. And you see the shape, which here is stretched out like that, and in summer it kind of contracts and moves towards the northern pole. And we do have some good explanation for that. Well, basically we see the area of large local memory contracts, it moves towards the pole, and the local memory strengthens overall, so the network is more robust in the summertime. And I have some similar results for the remote impact, but I think in the interest of time I'll skip over that. The key things are we can calculate important dynamic properties from our graphs of information flow that are actually relevant for climate scientists. And the results make intuitive sense. They're explanations, and you will see them in here. I also have an appendix slide at the very end of my talk if anybody wants to see that, because I think they will be posted on the web, and I also have the references there. And number 3 are they are for effects that are right now only vaguely known. We hope to soon provide more specific quantitative measures for that. So, for example, in the next slide you will see Actually, not the next slide. Okay. Well, so for example, what you saw before with the local memory. If the local memory and the remote impact go down, it means that I have less connectivity and the whole thing becomes less stable and less predictable. And climate scientists have known that would happen. Thank you. But now we hope that with these methods we can quantify it more. We can say, okay, in these areas it will happen, but towards the pole it will happen less than we thought. So we can now localize things. So I would just point out one more useful thing that we can do with this. So far we've only analyzed observed data. Now we're moving on to looking at the output of model data. And why we want to do that? Because we have models that at least give us some indication of what the climate is likely to be like 100 years from now. And so we can take the output of those models and analyze them and look at the information flow then versus now. And the question I sometimes get is, well, if we have a climate model, that must mean I have equations. And if I have equations, why do I have to take the output of the simulation? Why can't I just take the equations and figure out the information flow? So if you asked, why can't we just calculate the information flow directly from the equations? It's simply, we can't do that because the Earth is a very complex system, and the climate models are computationally intensive numerical models. So what you have is basically differential equations for fluid dynamics, etc. You evaluate them repeatedly on a 3D grid around the Earth, and until the model spits out the results, there's really nothing you can directly get out of that. Yes?
So all the data you get, you're manipulating on is from simulations before?
No, so far everything was observation.
Observation.
So far everything was observation. From now on it's going to be mainly model. Okay? Okay, so the next step we'll use model data, and I just wanted to make the point, there's really no other way to get information flow out of it rather than taking the output of the models and then looking at them. And again, I apologize, somehow these graphs don't look as crisp as they should. But what you see on the left side, this is again observed data for the period from 1950 to 2000. This is the CCS-M4 model for the same period. So this is simulation of what we think the climate looks like. And this is what it really looks like. And this is what we think it looks like in 100 years. And these are just very first results. We're just about to publish them. They come from one model and one model run only. So they only give us a tendency. This is not definite conclusions. But what we start to see is that these are relatively similar. But on this end, you see, especially in the tropics, there are a lot less errors around here. So the connectivity of my graph really goes down. This is, and I should say, these are what I plot as the average velocity of information flow that I obtained from the graphs. So the key points are, and again, the disclaimer, these results come from a single run of a single model. We're just now ready so that we can apply it to many of those runs and different models. But what it looks like so far is that the prominent mid-latitude information pathways in mid-troposphere weaken and shift poleward, and especially that the major tropical information pathways start diminishing. And averaged over the entire northern hemisphere, the atmospheric information flow weakens. And that weakening means that leads to reduced interconnectivity among different geographic locations, and thus a more chaotic atmosphere in the future. And again, especially around the tropics, less so around the poles. But again, the details are yet to be determined. After all the good news, I also want to share what's not so good about our method so far. Robustness. So if we change the significance level or the number of slices, everything is fine. It's very consistent. But we know the Ficata points only give us an approximative grid. So if I run this several times, the Ficata approximation algorithm, I get different grids. And I should get pretty much the same results for slightly varying grids, but I don't. So there is still too much variability if I change the grids. So that's something we definitely need to work on. And the temporary solution is we use 3 different grids and we compare the results. And we analyze the trends and use only what's consistent across all of the 3 different grids. But the long-term solution is that we really want to move on to high-resolution grids, and we're hoping that will solve our problem. I'm hoping that it's just because our resolution isn't high enough. So conclusion of future work. We now have a tool to track information flow in time and space around the globe. But it only scratches the surface of the understanding we can gain with this method. So the next thing we want to do is, number 1, is improve grid robustness. Number 2, increase grid resolution. We have 200 points. We want to have 2,000 points. And we're hoping number 2 will address number 1. And also, so far, we're tracking it just in a plane. We want to move to 3D information flow, so having at least 3 different layers there. And we want to apply to different variables. So far, we only had geopotential height. What do we get if we use something else? Can we use several and integrate them? And so just some algorithmic needs. I would like to have 2,000 locations on the globe instead of 200 in 3 layers, so I can do 3D information flow. That's 6,000 times 15 time sizes, so I would really like to deal with 90,000 nodes.
Take over, Joe.
And I think, Joe, you go for 40,000?
Yeah.
Well, I want even more. But the problem is the 3,000 one on my little MacBook Pro, that takes about 4 or 5 days. So my question is, how can we now move to that? So this is my last slide. My wish list for causal discovery research is number 1, methods that scale up to a very large number of nodes. Fast implementations. So I was thinking parallelized implementation in C. C tends to be faster than Java and MATLAB and R and all that, where the PC algorithm has been implemented. Especially efficient methods to learn temporal models. Maybe the PC algorithm isn't the way to go there. I don't know. And lastly, I would really love to see more tutorial papers comparing different methods. So, for example, I was delighted to see Joe's talk this morning and Frederick's talk yesterday, because that's, for me, really helpful. So which method is better for which type of problem and why, and especially what are the philosophical differences, and the whole thing written in a way so that somebody like me can understand it. So with that, that's the end. If anybody has any ideas of what else to try.
Well, one thing occurs to me about why you might be getting a lot of double-headed hours. I don't know if this is right, but in the PC algorithm, as opposed to the conservative PC algorithm, right, you get a triple of variables so that the connections between 2 are just strong enough to be detected. But when you go 3 out, they're weak enough because you have a multiplier effect that they look independent. And the algorithm puts double-headed arrows, or at least orients a collider in the middle, and you can get a series of double-headed arrows.
That kind of sounds like it could be exactly
So
what
it might be what's happening. So if you move to the conservative PC, you avoid that problem.
Okay.
And that might help you.
That's definitely worth a try and just see what's the difference. Yeah, great, thank you.
So do I understand correctly that what you did in the last part was essentially take the run of the physical models and
In the very
take
last
their
part.
numbers and then just give them to your search procedure?
Yes, that's correct.
So what have you talked with any of these finite element physical modeling people about your results? What do they think?
Well, besides for the climate change, I haven't talked to these people. But in general, in terms of taking the output from a model and doing this, they think that's the only way to do it. It's not. You can't go anywhere in between using numeric equations and learn anything from that. Is that your question?
Yeah, well, it was really whether they think the outputs are plausible.
Well, my climate scientist thinks it is. So he's really excited with us here. Let's publish this. Yes.
I have a follow-up question on Richard's, maybe about these instantaneous effects. So, how do I interpret a directed arrow from one?
If there's a 0-day delay or if there's a 1 day or
No,
higher.
0. With
If there's a 0-day delay,
They
well,
can
in a
be
few
written, right? Or
in a few cases it can happen. I mean, 0 days really means less than half a day. So
or
it can,
isn't this all measured at the same time? All this whatever thing you're measuring?
well, it's a question of how we're measuring information flow. I think that's the best way of thinking about it. We're trying to figure out how quickly and where and how information travels around the globe. If you look at weather as transferring information, it actually gives you a good guideline. You kind of can always figure out what's the maximal speed of wind, for example, and then you can figure out what is the maximum distance you can cover within 1 day and compare it to what you have.
But you measure wind speed at some time, right? Or is it an average over a day? Or what is it measuring?
The geopotential height, I think, is an average over the day. And so I'm really looking at, okay, I have a state here and I have a state here. How long does it take for this to influence this point, the state of this variable in some way? It's not directly linked to the winds that we're measuring. It's really the state change of geopotential height. Yes.
I have a question for you and Richard. When Richard said that the equator couldn't be a causal origin, right? Because
No,
it's
it's not quite that. It could be a causal origin if it doesn't vary.
Well, the
Then there
thing
would
is,
be
my question is this, it could act sort of like a boundary condition in a certain sense, but it might be doing it in an active manner. In other words, I don't know, high pressure approaches the equator, and the equator reacts in an active manner to keep the edge stable. So in other words, that it might be more or less constant, but doing so in an active manner. Would that not then be?
Well, the thing is, in causally, that's true, but in covariation, right? If you have one of the guys constant, then there is no covariation, just mathematics.
I was just going to say, if you look at it as information flow, well, if they are in the same state, then there's no information flowing.
Right.
So you shouldn't see
So
it.
it's like, the table is putting pressure on this all the time.
Right.
But you can't make any difference because it's still.
No, but if the table were, let's suppose the table were somehow vibrating, and then the pressure.
Well, no, I'm
Then you have
saying you need motion,
Then
you
you
need variation.
Yeah, but it's still putting the same pressure, average pressure on the table, even though, right? I guess there's a difference between.
It's a weird feature of the mathematics of covariation and what's going on in causal.
And it makes perfect sense here, again, if you think of it as information flow. Information flow means change. And if there's no change, there's no information flow.
When you look at the information flow, 100 years in
In the future.
In the future, you saw somehow more broken up information flow.
Yes.
I mean, isn't that the same kind of problem you had in economics when people tried to predict, the future of the economy, and then the bubble came along and it wasn't a mechanism that was in any of the models. So, I mean, couldn't there be new mechanisms in the future in climate that are just not going to be in your data, and therefore you try to predict in the future, you won't see coherence. But there may be more coherence actually than
I'm
you
not
would
claiming
allow.
that this is a time machine.
Yeah, okay, it's just a guess from the now, but then you always have that problem.
And again, it's only one model. There's about 7 different models around the world, really big climate models. And usually they give quite different results. What you do, you take the average.
Yeah, okay.
Think about that for a second, but I guess it answers
It's a
the question.
fundamental problem.
This analysis is based on the model output. So if the model is wrong, what we're getting out of it is wrong. But again, this is a tool to also evaluate the different models and especially see, okay, what does this model tell us about how things change and why is that? And then maybe compare the 7 different models, look at what they tell us differently, what the major differences are, and then you can go back to the drawing board and say, well, how should we change the model? So in addition to everything else, I look at it less as a time machine than something to evaluate the climate models. And that's actually a key issue. How do you evaluate climate models?
Yeah, I was along these lines. I was thinking if had you used anything to go back in time to predict something that had occurred,
Well, I mean, we have the model and we have the observed data for the period from 1950 to 2000. So you saw the 3 different plots next to each other. The 2 on the left, the very left one was the model, was the observed data, and one extra was the model. So these are kind of linking up, okay, which confirms the model.
Is there some way of actually using whatever constraints you find going back in time to help you going forward in time?
Hide the past.
Yeah.
Hide the past.
I'm
not sure if I...
Don't use it in your model. Don't put it into the estimation.
Okay.
And then try to go back.
I may be the wrong person because I'm only using the output from the models. I don't derive the models. And these are big national models that I have basically no saying, and I basically take what the climate scientists give me and say, run it on this. Yeah. Thank you.
One last question.
Well, yes, you actually this is a good thing. I was wondering about the interventions that you could do on the model. Could you do some interventions? And
Could you do some intervention on the model? And that's exactly what we're hoping to be, one of the things that comes out of it. We're hoping to better understand the inside of the climate models. That this will tell us something about assumptions in the climate models that we can then compare with other models and see which ones makes the most sense and how should these models be adjusted, these climate models.
I was thinking more about validating the causal findings by having events in your model that are disruptive.
Events that are
fake tornadoes or whatever.
Simulating, like simulating.
I can see it on a smaller scale. For this big scale, there's nothing I can do about the models. They are what they are.
Big hurricanes.